So we have an example on this page. Let's assume we have two relations. The first one is employee, right? We have SSN and name as attributes. And the second one we have here is a dependent. It's another relation. We have SSN and dependent name. And we want to do a natural join between them. So according to our previous page, we show that between them we find them they share a common attribute SSN, right? And we can define a natural join between employee and dependent as inside it we first calculate the product, right? Employee product with dependence. Then outside we have this select employee dot SSN equals to dependent dot SSN, right? Because this one is a shared attributes between them. And outside we further do a projection. We project SSN, name, and dependent name. Because this SSN is duplicated, we only have one record in AutoCount schema, right? We have only one SSN here. And formally we can represent the output of this natural join between these two tables as shown at the bottom. The schema is SSN, name, dependent name. We only have three attributes, right? Because this SSN is duplicated, we have only one record here in the AutoCount. And for all the data tuples, before we calculate the product, right, it will be 2 times 2. It should be 4 rows, right? However, we further check the condition. The employee SSN should be equal to the dependent SSN, right? Therefore, we have this record, this NX combined with this row crease remaining in the outcome, right? Similar for Brandy with David, as shown here. And the remaining one will be removed, right? And further here we do the projection to only get the 3 attributes out, SSN name and dependent name. The redundant SSN will be removed, right, by its projection. This is about natural join. And besides this, we can also do a very general case, and we can try to calculate the natural join between two relations. Let's assume we have two relations as shown here. We have a relation R with 2 attributes, A and B. We have a bunch of data instances inside this table. Another relation we have is S. In S, we have B, C as attributes. The B is shared with R, right? With C and C, they are shared attributes. Inside S, we have 3 data instances. We want to calculate the natural join between R and S. According to the definition of natural join, we know the calculation process may have 3 steps, right? The first step is to calculate the product. And we can try this example together. Let's calculate the product of these 2 tables first. And we want to calculate the product between R and S, right? And we can represent the table. We have 4 columns. We know this, right? As to the data tuples, we have 4 times 3, right? It should be 12. And we also need to have 1 row for the attribute names. Therefore, we have 13 rows, right? The first step will be calculating the. Let me write down the steps here. Step 1 will be R times S, right? So by doing this step, we can have the attribute name first, A, B, B, C, right? And we know the first row denotes the attribute names. Therefore, we have this highlight. We have a corner for them, right? And inside this tuples, we will combine each rows in R and each row in S, right? Therefore, we have this X, Y, right, combined with Z, U, right, and V, W, and Z, V, right? And this 2 will be the same, right? So this is for the first X, Y, we'll combine with all the tuples here. And we will combine X, Z with the ones we show here, right? Therefore, we have the remaining rows. But here we need to change this Y to Z, right? Similar here. we need to change this one to Y, as well as this one to Z, and the remaining 3 rows, right? This one should be Z, this one should be V, right? Okay, so by doing the step 1, we calculate the product between them, we can get a table like this, right? And besides the step 1, we do the product, we also need to do the selection, right? We can just borrow the operation we use here, right? Or have the selection here. We need to change this R with the B, right? Because the join attributes with B, right? Because they're shared by I and S. We know this R dot B should be equals to S dot B, right? These are the shared attributes. And we examine all the data tuples we have. We check if this RB equals to SB or not, right? We check each row. This one, no, right? In other words, this row should be removed. We can just cross it first, right? Because this R dot B is Y, S dot B is Z. They are not equal to each other, right? They should be removed. How about this one? No, right? Remove this one as well. How about this one? No, right? And this one? Yes. This one? No, right? This one? Yes. This one? Yes. This row? No, right? They're different. This row? Yes. This row? No, right? They're different. This row? Yes. This row? No, right? So by examining all the rows, we compare the B attributes from these two tables to check if they are the same or not. This one should be removed. This one 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 removed. As well as the last one, right? They should be all be deleted. And by doing this select, we can get a table like this, right? For the remaining data we have in the table, they agree with each other on a B value, right? So this is the second step. Besides this, we need to do a further projection, right? We need to do a further projection by using the pi here. We know the join attribute is B, and the remaining attributes will be A, B, C, right? B is duplicated. We have only one record of B here. Therefore, we can have this pi as our style operator, and we have the pi works on this selection results. Let me change format. And we have the attributes to be a project will be A, B, and C, right? Therefore, for the table we have here, we need to delete one column, right? Either one or this one, it doesn't matter because they agree with each other, right? Whichever one we can delete, it doesn't matter. For example, we can delete this column here, and this one will be the result we can get by doing the step 3, right? And this table will also be the output for the natural join between R and S. And we can compare two slides and compare with them with the table we show in the slides. We have 3 columns and we have 5 data tuples. Okay, let's compare the slides. This is the example we show here, right? We calculate the natural join between R and S. We also do the step-by-step for you in the example. This is the result we can get. It is the same as the one we showed before. I hope this example can show you how to calculate the natural join between 2 relations. And you can also try this to calculate it by yourself on papers after class. It will be helpful for you to have a deep understanding about the natural join. And we also have a joke about joins, right? A join query works up to 2 tables in a restaurant and asks, mind if I join you? I hope you can understand this joke, right? So, okay, this is about the joins. Join is very useful and important in the database design for the queries. I hope you can understand what is the join and how to calculate the join. This will be very important for the SQL to be learned later as well, because later we will work on lots of tables and we have to use the join to combine them together, right? So join is important, and you can try to go over all the slides again to make sure you can follow these materials.